Here we have two particles A and B, and we are going to consider the velocities of those two particles relative to a point O. O we imagine to be a point that's fixed on the ground. So we could call these velocities the actual or absolute velocities of the particles. Actual meaning relative to the fixed earth actually. Later on we will look at the velocity of B relative to A. Now at t equals 0, the initial time, particle A coincides with the origin O. Now I will start the timer soon, and it will be easy to see that the gap between the particles will open up because B has greater velocity than A. So let's start the timer. Now t here is shown in slow motion. It's meant to be in seconds, of course. I'll just pause it here. Now it shouldn't be too difficult to see that the gap between these particles will increase by 1 meter per second. So B will appear to move away from A by 1 meter per second, since the difference between these velocities is 1. So here is the notation for the velocity of B as seen by A. So we imagine that we are riding along with point A. Our coordinate system is fixed to point A, so A appears fixed to us, but B appears to move away from us by 1 meter per second. So the velocity of B relative to A, written VBA, is VB minus VA. So I'm going to show vector VBA. So I will rewind the timer to 0. Here is another example. In this situation, the velocity of A is greater than the velocity of B. The velocity of A is 3 meters per second, which is 1 meter per second greater than the velocity of B. So let's just run this timer. So obviously A is going to catch up with B and eventually overtake B. The gap is closing by 1 meter per second. I'll just pause it here. I'll rewind the timer. Okay, so we apply this simple formula to get the velocity of B relative to A. We take the velocity of B, which is plus 2, and subtract the velocity of A, plus 3, to get minus 1. So down here we have the relative velocity vector VBA. It's minus 1, so it's pointing to the left. So the speed of B relative to A is 1 meter per second. Now in this example we will consider the case where particle A approaches but never reaches particle B, and we will be interested in the distance of closest approach of the two particles. So let's see the simulation. So A is approaching B but never reaches B. The gap between them becomes a minimum, and for subsequent times the gap opens up. I'll pause it here. Here we see the velocities are not constant. The velocities of the particles vary with time. Let's look at the velocity of particle A. We can compare this formula to u plus at. So the initial velocity u of particle A is plus 2. We can see that here. At t equals 0, the velocity is 2. The acceleration is the coefficient of t, which is 0.5. Let's look at particle B. Its initial velocity u is plus 1, smaller than the initial velocity of particle A, but its acceleration is greater. Its acceleration, the coefficient of t, is plus 1. Here's the relative velocity, VBA. So we take 1 plus t and subtract this, and we get this expression, minus 1 plus 0.5t. Now this expression is negative for early times. We can see that at t equals 0, we get minus 1. So VBA is a negative vector. So for early times, B appears to approach A. So let's see that B appears to approach A. At some instant, B appears to stop, and for subsequent times, B appears to move away from A. So let's look at the time again when B appears to stop. So when VBA becomes 0, I'll just get that value. Okay, when B appears to stop, particles are at their closest, and we are interested in that time. So we are interested in the time when vector VBA is 0. But if VBA is 0, it obviously means that VB equals VA. So the particles are closest when the velocities are the same. When we solve the equation VA equals VB, or solve this equation here, difference is 0, we get t equals 2. Now we will consider the distance between the particles at any time t. In our example, the distance between the particles at time 0 is 5 meters. We will get a general formula for the distance between the particles at any time t, and we can use an alternative method to find the minimum distance between the particles. Now let's look at the situation some time t later. So SA is the position vector of A, SB is the position vector of B. We're going to consider the distance between the particles. So we want this vector here, that's vector SB minus this vector. So let's get vector SA. Well, at time t equals 0, A is at the origin. So we can just use this, we don't have to add anything on. We will for B, because at time t equals 0 we saw that B was 5 meters from the origin. Okay, so what's UA and AA? What's the initial velocity of A? Well, that's this value here. This is UA, of course, and this here is the acceleration from V equals U plus AT. So we've 2t, and we've half a 0.5. Half a 0.5 is 0.25. Okay, similarly for SB, but we must remember to add on the position of particle B at t equals 0. The initial position we saw is 5 meters. So when t is 0, we just get SB equals 5. That's what we want. So the initial velocity is 1. The acceleration is 1. Now, let's get an expression for the distance between the two particles. So we have this expression minus this. T minus 2t is minus t. Half minus 0.5 is 0.25. And we 5 minus 0 is 5. Of course, we can write the square term first, just the standard form for a quadratic. Alright, so here's our expression for the distance between the two particles. Now, we're going to find the value of t that minimizes this by using calculus. So let's consider the graph of this distance. Well, we know that at t equals 0, the distance is 5. Indeed, if we plug 0 in, we get 5. And that was what we saw earlier. That's the initial condition for the particles. So what happens as t increases? Well, we know that the particles approach each other. So the distance between the particles decreases. Keeps on decreasing until it reaches a minimum value. The particles never meet, so this graph doesn't hit the origin. And after the distance of closest approach, the particles move apart. Well, B moves away from A, as we've seen. Okay, so here's our quadratic. Okay, it's a parabola, of course. We know that at t equals 2, the distance is a minimum. But from calculus, we can find that minimum by considering the derivative. The slope of the curve is 0 at the minimum point. So we take the derivative of this quantity, which gives us 0.5t minus 1, and we want the slope to be 0. Okay, at the minimum point, the slope of the curve is 0. And if we solve this, we get t equals 2, as we saw before. Now, if you don't know any calculus, you can still find the minimum value of this function, or the time that gives the minimum value of this function, by completing the square. Okay, so I've taken this quadratic and factorized out 0.25, and we get this in here. So to complete the square, what you need to do is look at the coefficient of t, half it. Half of minus 4 gives you minus 2. Okay, then what you do is you take t minus 2 and square it. Now if you square that, you're going to get back the first two terms. You're going to get t squared and you're going to get minus 4t. And as for the constant term, well, that's going to be plus 4. You know, minus 2 squared is plus 4. So to get to 20, you'll have to add on 16. Okay, so you have half the coefficient of t. Write your quadratic as t minus that t plus that value squared. Okay, t plus half the coefficient of t all squared, and then you have to make up for the difference because you want to get 20. Now if we look carefully at this thing, when is this a minimum? When is this function a minimum? Well, we can see that t minus 2 squared is always greater than or equal to 0 because it's something squared. So everything inside here is always going to be greater than or equal to 16. So everything highlighted here will be a minimum, i.e. it will equal 16 when this thing in here is exactly 0. Okay, this thing cannot be any less than 0 because it's something squared. So when is this equal to 0? Well, t minus 2 equals 0 when t is equal to 2. Okay, that's just an aside. So we found the time, and now we can go and find the closest distance between the particles. So that's straightforward. We just take our value of 2 and just plug it into this. So you get that the minimum distance between the particles is 4 meters. Now using calculus we can consider the general situation. So we are interested in the lowest point of this curve, which gives the minimum distance between the particles. So we know what to do. We take the derivative with respect to time, set that derivative equal to 0 and solve. But differentiating this quantity is equivalent to differentiating SP and SA separately and subtracting. Okay, we're just subtracting functions. You can just differentiate each function. But here's SP. Okay, now the initial position of SP we saw in our example was 5 meters, but it could be any value, of course. If we take its derivative with respect to time, we just get the velocity. Okay, we just have a constant times t here, so the derivative of that is just the constant. And differentiating this term gives us acceleration times time. So here's the familiar formula for velocity: v equals u plus at. If we differentiate this quantity, which was 5 meters in our example, we just get 0 because this is just a constant. It's just a number. It doesn't depend on time. So this derivative is vb, and similarly this derivative is va. So we've the difference of the velocities, but that's just relative velocity. This is the velocity of b relative to a. So we can see that we get the condition for the closest distance that we saw earlier. Of course, this is the same as saying that the velocities are equal.